We're going to discuss half-life and radioactive decay today. This is kind of a follow-up on our last video discussing also radioactive decay. So we'll just talk about the process of half-life today. Half-life is an interesting concept. It's one we even use in other sciences, biology, archaeology, and we use half-life to find how old something is. If you've heard of carbon dating, that's using, we use the half-life of something. So it's a pretty simple process. It starts with an initial amount. So we have some initial amount, we would call that 100%. After the first half-life, we have, can you believe it, half of the original amount, or 50%. And then keeps going. After the second half-life, you would have 25%. After the third half-life, you would have about 12.5%. After the fourth half-life, you would have 6.25%, and then let's see if I can do the last one. After the fifth half-life, you would have 3.125%, right? So notice we're just exponentially getting smaller and smaller and smaller, closer to zero. So we could even take something like this, our three different types of decay. We've talked about alpha decay, we've talked about beta decay, and we've talked about gamma decay, and we could put some numbers to this. So let's go, where'd it go? Here we go, let's go here. So say we had 50 grams of uranium, and we found out right here that uranium-235 has a half-life of 700 million years. So what does that mean? It means that it would take 700 million years for 50 grams of uranium, I'm going to put one half-life over here, to turn into 25 grams of uranium, right? So what happened to those 25 grams? Well, if you looked at our alpha decay problem, it would take, again, 700 million years for 50 of these grams, I won't say disappear, but to become thorium. That's what happens. One nucleus is moved, is transferred, is turned into another nucleus. That's what's happening in half-life. That's what's happening when nuclei decay and break down. All right, so moving on, we can look at this graphically as well. So here we have a substance, we can say uranium as well, and we can look at a graph and figure out what the half-life is. This may help some people who are a little bit more visual. So I always have to know my starting amount for a substance, right? And it would make sense that my starting amount would be at 0 years or 0 whatever. So on the graph, I see that my starting amount is 10, we'll say grams here, 10 grams. So my starting amount is 10 grams. I always like to write down what I'm starting with. And if I want to find the half-life of this substance, what do I need to do? Well, I need to take half of 10 grams, and half of 10 grams would be right here on the graph. This would be 5 grams, right? So if I wrote this out, and we'll do this in a second when I start writing the problems, I like to write it like this: 10 grams after one half-life becomes 5 grams. Now we still didn't answer the problem. What is the half-life? Half-life is a measure of time, so it's really easy. I can now take my graph. I won't get a straight line here, but I can go bam to there, and I can go down, and this looks to be a half-life for this substance is going to be about 30 years. So that's one way we can figure it out graphically, and you'll certainly see that on your test. Okay, so let's do a few problems. All these problems are very similar. We're using the same process, but we'll go through 3 different problems here. Okay, I like to annotate my problems. So as I read, I'm going to circle, underline some things, and I think that helps. If you start with a 120 gram sample, that's a given, of radium, how much will be left after 44 days? And the half-life is 11 days. Okay, so my first step is I always want to know my starting amount. And my starting amount is 120 grams. So I'm going to write this down. But I forgot one thing on my problem. I needed to circle how much will be left, right? How much means we're talking about something in grams. My answer is going to be in grams. Okay, super. So I have my starting amounts. I know my final answer needs to be in grams. The next thing I need to know is how many half-lives do we have, right? We know it's 44 days is the time period we're looking at, but a half-life is 11 days. So the first bit of math we need to do is 44 days divided by 11 days is going to give you 4 half-lives. So once we have this information, we're good to go. We can figure out the problem. And again, I use the same setup every time. I do like this, 120, our first half-life, we're going to have half of that, which is going to be 60 grams. Our second half-life is going to go from 60 to 30 grams. Our third half-life is going to go from 30 to 15 grams, and we have one more half-life. It's going to go from 15 to 7.5 grams. And it says after 4 half-lives or 44 days, how much is left? That is our answer, 7.5 grams. Looks logical to me. Okay, let's do another one. An 80-gram sample of 3H that's called tritium decays, leaving 2.5 grams of 3H. How long would this take? So let's annotate our problem. I'm given 80 grams. I'm also know that there's going to be 2.5 grams remaining. How long would this take? So just logically, I'm thinking that my answer is probably going to be in years. It's some unit of time. And our half-life of tritium is 12.3 years. Okay, so let's always start with what we know our starting amount, right? So we're starting with 80 grams. And we need to figure out how long this would take, right? So we need to figure out time, right? So we know also that there's 2.5 grams left. Okay, so let's start doing some half-lives here. I'm going to do my first one, 80 grams. It's going to become 40 grams. 40 grams after 2 half-lives is going to become 20 grams. Sorry, I need to put grams there. 20 grams after 3 half-lives is going to become 10 grams. 10 grams after 4 half-lives is going to become 5 grams. And look at this, after 5 half-lives, 5 grams is going to be 2.5 grams. So we're almost there, 80 grams decays, leaving 2.5 grams. How long would this take? Well, it looks like it took 5 half-lives. Well, that's great, but we want to be a little more specific than that. We know a half-life is 12.3 years. So let's just do a little multiplication. 12.3 years times 5 half-lives. And if we do the math here, we should get, well, I'll just do the math instead of cheating. We should get 61.5 years. And does that make sense? Is that logical? Yeah, after 5 half-lives, it would take 61.5 years to go from 80 grams to 2.5 grams. That makes sense. All right, let's do one more. I start with 200 grams of thallium-207, so let's annotate as usual. 200 grams of thallium-207 after 20 minutes. If I can find my... After 20 minutes, there's only 12.5 grams of thallium left. What is the half-life of the decay process? Okay, so let's start with what we always do. 200 grams is my starting amounts. It says after 20 minutes, there's only 12.5 grams of thallium left. Let's go through and do some half-lives here. So 200 to 100 is going to be our first half-life. 100 to 50 is going to be our second half-life. 50 to 25 grams is going to be our third half-life. And then 25 to 12.5 grams is going to be 4 half-lives, right? So it says, what is the half-life of the decay process? Notice half-life is going to be in years. They don't want to know how many half-lives. They want to know what is the half-life. What is 1 half-life? So what do we do here? Well, we know that 20 minutes is how long this process took, right? We start with 200 grams. After 20 minutes, there's only 12.5 grams left. And we found out that 4 half-lives took 20 minutes, right? So 4 half-lives. So if I divide the two, if I can get my eye here, that would tell me that each half-life was 5 minutes, and that would make sense. The half-life is 5 minutes. There's 4 half-lives. That took 20 minutes, and we see the process where that happened.